Swayam Prabha. Digital India. Educated India.
We will now move on to another type of hypothesis, hypothesis number 2, which is called testing linear restriction. Testing linear restriction. For that, what we will do, we will take that that same production function where log of y I equals to alpha plus, let us say, beta 1 log of lever plus beta 2 log of capital plus ui. This is the kind of production function that we are hypothesizing, and we are testing linear restriction. Basically, let us say our null is this beta 1 plus beta 2 equals to 1. Let us say this is our hypothesis, this is our null. Now, what is the meaning of this? Once again, we need to understand, when you are testing the validity, this is testing the validity of linear restriction actually. What is the meaning? So, testing validity of linear restriction means, let us say beta 1 equals to beta 2, beta 1 plus beta 2 equals to 1, that is what we are going to test. What is the meaning of this? If this is a production function, then beta 1 basically indicates returns to lever, and beta 2 indicates returns to capital. Okay. And if you take summation of these two, beta 1 plus beta 2, then that is what, that means returns to lever plus returns to capital. Okay. And this has a different name. When you add returns to both the factors, then as you know from your understanding of microeconomic theory of production function, that is basically called returns to scale. That means when both the factors are changing, then it is called returns to scale. When one factor is changing, that is called returns to factor. And as you know, in a production function, we may have three alternative cases: increasing returns to scale, decreasing returns to scale, and constant returns to scale. So, our claim, what is our claim? Our claim is, let us say, production function exhibits non-constant returns to scale. Non-constant returns to scale. Okay. We do not know whether it is IRS or DRS, but at least our claim is that it is not constant. And then when you nullify that claim, okay, so that means our alternative is basically, alternatives are two types, beta 1 plus beta 2 could be either this or beta 1 plus beta 2 could be either this is IRS and this is DRS. So, we are hypothesizing actually the possibility of these two cases, that is our claim, and when we nullify our claim, our null becomes beta 1 plus beta 2 equals to 1, constant returns to scale. Okay, constant returns to scale. If that is the case, then how will you test? So, first we will follow, there are two approaches. The first approach is, this is first approach, I will write this is as first approach. Where I am going to use t statistic, using t stat. So, your null is this H naught beta 1 plus beta 2 equals to 1. Okay. All right. So, if that is the case, then how will you formulate your test statistic? So, it would become estimated value of your population parameter, that means beta 1 hat plus beta 2 hat minus hypothesized value of the population parameter. So, that means this first I will write beta 1 plus beta 2 divided by standard error of beta 1 hat plus beta 2 hat. That is what we learn. Now, hypothesized value of this, what is the value? We have hypothesized beta 1 plus beta 2 equals to 1. That is why your numerator would become beta 1 hat plus beta 2 hat minus 1 divided by standard error of beta 1 hat plus beta 2 hat. See, this test statistic expression is little different from the earlier cases. Earlier, we used to write beta 1 hat plus beta 2 hat minus 0 or beta 1 hat minus 0 divided by standard error of beta hat. So, that means in general, when nothing is mentioned, we hypothesize the value of the true population parameter is 0, because our objective is to test the statistical significance of the variable, whether a particular variable, whether the particular coefficient is statistically different from 0 or not. That is our hypothesis. So, obviously, if that is the hypothesis, then what will happen? It would become minus 0, but here this is different. It is beta 1 hat plus beta 2 hat minus 1, because we are hypothesizing the value of the true population parameter is 1. And what is the population parameter here? It is beta 1 plus beta 2. And again, what is the standard error of beta 1 hat plus beta 2 hat? It is again square root of the variance. So, this would become beta 1 hat plus beta 2 hat minus 1 divided by variance of beta 1 hat plus variance of beta 2 hat plus 2 into covariance of beta 1 beta 2. And once again, after doing all this, you will get a t value which is called t calculated. And if that is greater than t tabulated, so this will follow a t distribution with n minus k degrees of freedom, and this would be t tabulated. If this is this, then reject our null. And what was your null? Beta 1 plus beta 2 equals to 1. When you reject your null, you can only say the production function exhibits non-returns to scale. But you are not sure whether it is increasing returns to scale or decreasing returns to scale. So, when you reject your null, you can only say that production function exhibits non-constant returns to scale. But which particular non-constant return you will get, that depends on if beta 1 hat is greater than beta 2 hat, okay, or sorry, if beta 1 plus beta 2 hat, if beta 1 hat plus beta 2 hat is greater than 1, then we will say that this is IRS. If beta 1 hat plus beta 2 hat is less than 1, then we will say that DRS. So, that depends on, that means once you reject your null, then in the second stage you have to see which particular case, that means you have to see the value of beta 1 hat and beta 2 hat, you sum it up and then see if beta 1 hat plus beta 2 hat is actually greater than 1, then we will say that the production function exhibits constant returns to scale. If beta 1 hat plus beta 2 hat is less than 1, then we will say that production function exhibit diminishing returns to scale. So, that means immediately after rejecting your null, you cannot say anything. Immediately after rejecting your null, you can only say that production function exhibit non-constant returns to scale. After that, you will look into the values beta 1 hat and beta 2 hat, you will sum it up, then you will see which among these two alternative cases actually is suitable in a particular context. That is how you need to apply your T statistic to test this type of hypothesis. This is the first approach. There is one more approach to test this hypothesis, and that is the second approach. And the second approach is known as restricted least square approach. Using F. So, here restricted least square approach will use F statistic. So, I will write the production function once again, log of yi equals to alpha plus beta 1 log of lever plus beta 2 log of capital plus ui. Okay, and your hypothesis, what is the hypothesis that we are going to test is H naught beta 1 plus beta 2 equals to 1. Now, this least square, restricted least square approach, this alternative approach says, if you want to test this, you impose this restriction in the production function itself and then derive a restricted version of the production function, and then you derive your test statistic, and then you check the validity of such restriction. So, what they are saying? You impose the restriction in the production function, derive a restricted version of the production function, estimate your test statistic, and then you see the validity of the restriction. Okay. So, what I am saying, the first step is impose the restriction in the model, and second step is then derive restricted model, then you compute your test statistic, to check validity of such restriction. Okay. So, that means what I will do, I will impose this restriction here. So, if you how can you impose the restriction here? If beta 1 equals to beta 2, sorry, if beta 1 plus beta 2 equals to 1, that implies that I can say that either beta 1 equals to 1 minus beta 2 or beta 2 equals to 1 minus beta 1. So, what I am saying? I am saying, let us say beta 2 equals to 1 minus beta 1. Beta 2 equals to 1 minus beta 1, right. Then you impose this restriction here. If we impose the restriction, then we can say that log of y I equals to alpha plus beta 1 log L plus 1 minus beta 1, sorry, 1 minus beta 1 log k plus ui. So, this would become alpha plus beta 1 log L plus log k minus beta 1 log k plus ui. So, you can take this log k this side. So, that would become log y minus log k, and this would become log y minus log k, which will in turn become log of yi by k equals to alpha plus beta 1 log L minus log k, which you can write plus log of L by k plus ui. Let us say this is our restricted model. So, this is our unrestricted model, and this is our restricted model. Okay. All right, this is the restricted model. What we have done? We have simply imposed the restriction. You can also put here, I have given beta 2 equals to 1 minus beta 1. You can say that beta 1 equals to 1 minus beta 2. You can derive another version of restricted model. Then the next step is, once you estimate, so next step is estimate both restricted and unrestricted model using OLS. And when you estimate the restricted version of the model using OLS, that is known as restricted least square approach in the literature. You can remember this name in the literature whenever you are estimating a model, restricted version of your original model using OLS, it is known as restricted least square approach. So, estimate both restricted and unrestricted model using OLS and collect RSS residual sum of square from restricted model, residual sum of square from unrestricted model, also R square from the restricted model and R square from the unrestricted model. Once you collect this residual sum of square and R square from both the models, you will have your test statistic using this formula. What would be your test statistic? Your test statistic F is defined in this way: RSS R minus RSS UR divided by M, where M is number of linear restriction. What is the number of linear restriction here? That is 1 divided by RSS UR divided by N minus K, where K is the total number of parameters in the unrestricted model. Okay. Now, you may get sometime confused that in the numerator, should it be RSS R minus RSS UR or RSS UR minus RSS R? You have to keep one thing in mind, that this is the relationship between RSS R between RSS UR. The restricted RSS, that means RSS from the restricted model, is always greater than or equals to RSS unrestricted. Why this is so? When you are imposing restriction, you see in the restricted model you have only one explanatory variable, that is L by K. However, in the unrestricted model you have two explanatory variables. So, obviously, when number of explanatory variable goes down, the RSS would become higher, that is, or at least higher or equal, at least it will not come down. So, that means RSS in the restricted model should be more than or equals to RSS UR, since in the restricted model you have less number of explanatory variable. This is F statistic you can calculate using the RSS. If you want to get a R square version of this formula, then that would become like this. So, RSS R you can write as, that means this would become R square. Now, among R square UR and R square R, you can easily understand that R square in the unrestricted model should be greater than, this would become M and this would become 1 minus R square UR. Why am I writing this? Because R square UR is greater than or equals to R square R. That is also clear, because in the unrestricted model, since you have more explanatory variable, your R square is higher, because R square and RSS, there is some kind of inverse relationship. When R square increases, RSS will come down. When R square decreases, RSS will go up. That is the relationship between R square and RSS, and that is why if this is the RSS version of the formula, this would become the R square version of the formula. Okay. And then again this will give you F calculated, okay, F calculated, which will follow a F distribution. What would be the degrees of freedom? M for the numerator and N minus K for the denominator. Okay. And if this calculated F is greater than F tabulated, at these degrees of freedom and 1% or 5% level of significance, then reject your null. That means beta 1 plus beta 2 hat, beta 1 plus beta 2 equals to 1, that hypothesis you can reject. And if you reject this, then depending on the values of beta 1 hat and beta 2 hat, you will decide whether there is increasing returns to scale or decreasing returns to scale. Okay. All right. So, this is basically the idea of restricted and unrestricted models of computing your F statistic, right. So, with this we are just closing our discussion on hypothesis testing. Next day what we will do, we will take some data set, preferably the production function. We will estimate the production function and then we will test these two important hypotheses, equality between two regression coefficient and beta 1 hat plus and the validity of a linear restriction. So, these two we will test using a simple data set in our next class. Thank you.